Okay, hi everyone, my name's Edwin and I'm going to talk to you about a library that we've been working on to make programming with index data types just that little bit nicer. So this is joint work with Guillaume Allais in St Andrews, Ohad Kamar in Edinburgh and Jeremy Allop in Cambridge. So it's a library that Ohad has probably done the bulk of the implementation work. My contribution to this is largely making Idris 2 good enough to support the library work that Ohad has been doing. So I'm going to present to you how this library helps specifically for Idris 2 programming, and specifically how it improves or how it aims to improve programming with index data types in Idris. So I'm being specific about the aims to improve because this is very much a work in progress. So we've made some significant progress on getting the core of the library working and getting some of the basic examples that illustrate the ideas working. But as you'll see, there's still a fair way to go. So it's about supporting computations in index positions and data types. So this is something that if you've done much dependently typed programming, you'll see that this is the kind of thing that comes up quite regularly. And you end up having to prove some small lemmas or do some rewriting in the data types to show that the program that you want is a program that the machine should accept. You always feel that it's more work than it should be. So if you're in a situation where you have some proof of x plus y, and what you really need is a proof of y plus x. You think, do I really have to explain that to the machine? So the goal with Frex is that you no longer will have to explain that to the machine. So there's an implementation of it. It's currently implemented in Idris 2, and in fact, Idris 2 is a new implementation of Idris that I started working on a couple of years ago, and it's now got to a point where it's really the recommended way to do Idris programming. So although there's still a long way to go, significantly better than Idris 1 in terms of robustness and efficiency. And Frex is really been one of those a library that has driven the performance improvements that have been needed in Idris 2 to a large extent. So it's probably the first significant thing that's been implemented in Idris 2 other than Idris 2 itself. So it's been an excellent test of Idris 2's performance. Because doing computations in index positions, there's a lot of type level programming that needs doing. However, it's not specific to Idris. So the things that I'm going to talk about today are things that you would certainly be able to implement in other dependently typed languages. So we imagine implementations for Agda, Coq, Lean, name your favorite dependently typed system. Hopefully you'll be able to adapt these ideas. Actually putting it into practice in everyday programming, that probably is something that's going to be a bit more specific with the different language implementations, but the library itself is not. So, just to illustrate the sort of problem that we're trying to help with here. So when you're doing dependently typed programming, you're allowed to index data types by some property of that data. So everybody's favourite first dependent type is lists indexed by length, so vectors have lengths. Alternating lists, this is going to be my running example throughout this talk. So alternating lists, this is a list where you have the types of the elements at even position, the types of the elements at odd position, and to know what the type of the first thing in that list is going to be, we have to know what the parity of the current position is. So we're even and odd types, and we're going to say what the start of what the start parity is, so the parity of the next element, and then the parity at the end of the list. Or maybe so something I did several years ago was an attempt to implement to reason about some aspects of hardware design with dependent types. So we could represent binary numbers as being indexed by the NAT equivalent, and then you could say because unary addition is correct, binary addition being indexed by unary addition, binary addition is correct. So you could implement a carry ripple adder in this binary data type indexed by the NAT underneath, and you'd know you got it right. So by indexing things by some property of that data, when we write operations on the data, the types of those operations will capture the properties of those operations. So if we're appending two vectors, so we've got a vector of n things, a vector of m things, the type of append tells us we have a vector of n plus m things. Perhaps more interestingly, if we're adding binary numbers, if we've got a binary number n and a binary representation of m, then adding the binary representations will give us something corresponding to addition of the natural number addition. So this looks like a thing, it looks like a really appealing thing, that to get this kind of property in a program and know that the program is going to do what we want it to do, at least as far as these abstract properties that we've captured in the type is concerned. But if you've had any experience at all of dependently typed programming, you will quite quickly have run into difficulties. So let's take alternating lists as an example, and all we're going to do is try to implement a function which concatenates two of these alternating lists. So that's already going to have some difficulties, like we're going to have to make sure that when we concatenate the two, that the parity lines up so that we have the even and the odd elements next to each other. So we're only going to be able to concatenate things of the appropriate forms. So this is something that we keep track of in the type. We say that an alternating list, it has its two element types. We've got a start the start value and the current parity. So that's essentially a number 0 or 1. So this fin2 is a number bounded by 2. So an empty list has is a parity 0. If we want to add an element to a list, well, we need to know what the parity of the tail of the list is, and then the element that we're adding at the front has to be the opposite parity. So choose says if we're at parity 0, we need the even type. If we're at parity 1, we need the odd type. So as we go through the list, the parity is going to be changing. So we're going to get alternating elements. So so an alternating list could be we're alternating booleans and strings. So true, tidy, false, Idris 2, and that's starting at parity 0 and ending at the same parity it started at. So let's try concatenating them and look at what the type of that needs to be. So if we've got a list with a start parity and then the ending parity of the left list, then the next list the list that we concatenate onto it, as I say, this has to have an appropriately corresponding parity in order to be something that we even can concatenate. So we have in the index here that the second list that we add needs to have a correspondingly calculated parity, and as a result we will have something that's with the same start parity, and then the ending parity is going to be whatever the parity of the left thing was plus whatever the parity of the right thing was. So it's sort of like saying what the length of the list is in the way that we know and love with vectors, but this is going to be mod 2 addition, so it's always going to be 0 or 1. And what we'd like to do is just write our concatenation function in the same way that we always do for any other list. So the usual thing of nil plus y's just gives us y's. The usual thing of x cons x's plus y's will recursively concatenate x's and y's and stick an x on the front. Unfortunately, this isn't well typed, and it looks like it should be. It looks like a perfectly reasonable thing to do, but we need to explain to the machine why these additions have us in the right place in order to, so in the nil case, we're in the right place to put y's on the front, and in the cons case that we're ending up with the right length and we're at the right parity at this point. So, so even this little example we've already run into trouble. And the more expressive indices you have, the more involved the proofs are going to get. So thinking of the binary example, so this is something I did many years ago, trying to do the binary adder, and we were able to implement the binary adder by having a very long series of rewrite tactics that just did the equational reasoning. So, but even for a small problem like this, we have a surprising amount that we need to prove. So a trick that you can use, and this isn't specific to Frex, but it's something that we take great advantage of in Frex, is the idea of fording. So fording is, so this is a term introduced by Conor McBride quite some time ago as a technique for implementing programs with tricky behavior in the indices. The basic idea is you replace the expressions in the indices with a for all bound variable, so that's you can have any one of these that you like, and we'll constrain that variable with some constraint that restricts what that variable could be, hence the name fording. You can have any index as long as it's 1 plus start, for example. So you can have any index as long as it's start plus left. So rather than, in this case of concatenating lists, is rather than saying start plus left here, we will for all bind it, and then we'll give a constraint that it must be equal to start plus left. So we'll start by fording the alt data type. So there's nothing to change in nil. But in the case of cons, anytime we see an index with a slightly more complex expression, we're going to replace that with a bound variable, and then we're going to constrain that variable. So we've replaced the 1 plus start in the tail of the list with some variable p. We've replaced the 1 plus parity in the return length with the variable q. And then we've given these two equality constraints that p must equal 1 plus start, q must equal 1 plus parity. We've got the auto keyword here. So the auto keyword is a way of saying to Idris, I want you to implicitly calculate what this is going to be. So I want you to calculate this at compile time, and it will try to construct a proof, which we would hope would be REFL. So just building it as before would be REFL. The 0 here, this is new in Idris 2. This is Idris 2 implements some quantitative type theory. So as described by Conor McBride, Bob Atke in recent work, and the 0 means this is guaranteed to be raised at runtime. So when we introduce these constraints, we're not adding any runtime costs, we're giving just the additional constraint to compile time. So then what happens, we'll change this this append function so that instead of start plus left, left plus right here, we'll say that we have the property P is start plus left, the property Q is left plus right. Now that gets us part of the way, so that at least that changes things so that rather than the machine looking at equation and saying no, I can't solve this, that takes the equation and essentially punts it back to the user, punts it back to the programmer, and says to the programmer, you said this constraint had to be solved, you're going to have to provide a proof of that constraint. So the auto allows the machine to at least try to infer a solution to that constraint. If the machine can't do it, the programmer has the ability to put something in manually. So you start writing these rewrite tactics, you apply some rewrite rules, and then you get the program that you would have liked to write. So the advantages are that it makes the type checker's job easier. It's not necessarily the case that we want to make the type checker's job easier, because we want the programmer to be doing as little work as possible. On the other hand, this is making it possible to type check things that previously were unsolvable. So unsolvable constraints are given back to the user can provide the proofs. On the other hand, the user can provide proofs, but correspondingly the user has to provide proofs. and it's verbose. So the programs that come out, they're going to be noisy. There's some proof details that, while they're important, they're things that maybe the type checker should be able to do. And it gets in the way of what the program you're writing actually is. So the Frex library, the goal of the Frex library is to automatically discharge these propositional proof obligations. So we do this by encoding a new notion of equality as a library. So this is equality in a freely extended algebra, and we have a function called Frexify. So Frexify will take a description of the algebra. It will take a description of the equalities that we want to prove, and it will attempt to solve that. Basically by normalizing the two sides of an equation according to rules provided as a description of the algebra. If they have the same normal form, we have a proof. Off we go. So Frexify is a function that, given a Frexlet, so a Frexlet is, think of it as like an interface to your algebra that says what properties it has. So how to build expressions in that algebra, how to build terms in that algebra. What are the properties of them? So, for example, it could be, let's give the properties of commutative monoids. I say commutative monoids because that's the only one we've implemented so far. So more of these are, more Frexlets are work in progress. Commutative monoids are the ones we've implemented fully. So we give it a Frexlet, we give it an environment of the variables, so that's things like start and parity in our alt example. And we'll give it a pair of terms that we want to, or a representation of a pair of terms. And Frexify will give us back a proof that the terms are equal. At least that is, assuming it can construct the proof. So if it can't construct the proof, we'll get a compile time error. If it can construct the proof, then we've won, and we can carry on. So that's a description of what happens inside Frexify. So the type is, at first it looks a little bit scary, but it's really just encoding what I've described here. So we've got a Frexlet, which is describing properties of our algebra. We've got an environment, so these are references into, so we basically say what the variables are that we have in our equation. So this is going to be our start and parity, for example, and then representations of the equations. So these are either going to be variables, or they're going to be static values, concrete terms. Then if we manage, so this is going to be the proof that we need to feed it. If all is successful, this proof that we feed it is going to be REFL. If it's not REFL, then we've probably lost. And then what that gives us back is a representation, or a proof that that we can proceed. So our index data types that we're interested in are equal. So Frexlets, let's say for example, our Frexlet for commutative monoids. Frexlets will describe the properties of a structure. So those properties of a structure will be the primitive properties, so the primitive rewrite rules that we're going to be using to normalize our structures. Essentially what it's giving us is a way of normalizing some expressions in some algebra. Given that, we can apply Frexify to normalize the index of a data type. So we still have to do a little bit of work to explain which indexes we care about, which indexes we want to rewrite. But Frexify will apply those rewritings automatically. So this isn't completely free. So the implementations of a Frexlet, this is where we have to prove the various properties that we're interested in our structure. And Frexify is applying those rules, doing the rewritings as it goes. So that the rewrite tactic that you typically see in doing the equational reasoning is something that is built up. So applications of that rewriting are built up by running Frexify. So as an example, and so this is where we've got to, and you'll see here that this is partly why it's a work in progress. So there's some there's a little bit of extra work that the user has to do that we'd hope to be able to push onto the machine as we go. But where we're at is if we can describe the environment of variables that we're interested in, and we can describe some representation of a term, Frexify will do those rewritings. So so replace to, this is a helper function that says, so it's saying where to invoke Frexify. So because alt has two indices, we're interested in doing replacements in both of the indices. So we want to replace so that the start parity and the end parity. So we're going to apply Frexify for both of the indices. Here we're saying what the equations are we're wanting to rewrite, so what the target of the rewriting is. So this could be an arbitrarily complex expression as long as it's in a commutative monoid. And then this Frexify, this is the second index. And then assuming this succeeds, this will rewrite the types to the same normal form. We can now just return the list as we'd have hoped. So there's still quite a bit of noise here, and this is although this is where we're at. The noise here is in kind of manually translating the expression and turning that expression into something that Frexify understands. It's completely mechanical, and if something is completely mechanical, it's not something that a programmer should be doing. It's something that we should be able to explain to a machine how to do. So I imagine at some point a reflection mechanism, perhaps using elaborator reflection, which is a way of writing Idris programs to inspect types, inspect values, or inspect the structure of values, allows us to write programs by inspecting values. So basically meta programming. So imagine some mechanism that allows these calls to Frexify to be a case of quote the type and then run Frexify. So it's even worse in the case of in the cons case. Again, all we're doing here is asking it to rewrite the indices, and then you can pretty much see the program here. So the program we want to write is x cons x's plus y's, but we have to say when we're constructing the proofs that go into the forwarded version of alt, we have to say, oh, you need to invoke Frexify to get this to be what I think it should be, and similarly here. So we would rather hope that that the machine would be able to construct these calls to Frexify so that the programmer doesn't have to, but at the moment the programmer still has to write them. So partly this is part of why it's a work in progress, or part of what makes it a work in progress. So it's while it might look longer than the series of rewritings you would do, for more complex indices, well, firstly it's going to be shorter, but also it's because the way the language is set up, the language is not really set up to be dealing with reasoning about equations and types. So what we're having to do here is construct a thing that we'd ideally like to have in the type checker. Maybe something like you get with refinement types, where you're invoking an external SMT solver to do the proofs for you. So this is not something we have in the type system, but there's something pleasing about the fact that we can at least add it as a call to a function, even if at the moment it's a little bit noisy. So in our dream future, this is in our ideal future, this is these things go away. So, in summary, what we have, that's as far as we got, is being able to do these rewritings automatically. So we have the general machinery for implementing Frexlets and for rewriting expressions by applying Frexlets with Frexify. So it's given us this library, this general library for discharging proof obligations. We've fully implemented commutative monoids. There's plenty others still to come. So one thing to note is that this is extensible, so you're not going to be limited to just the things that we provide. As long as you're able to describe the properties, you will be able to describe new rewriting systems, and you'll be able to do those proofs automatically. And something I think is very nice about it is that if Frexify can't find an answer, that means there isn't an answer. So we're constructing normal forms of expressions here. So the fact that we're constructing normal forms of expressions means that this is, so it's sound because we're getting the proof, and it's complete because we're constructing normal forms. Still a lot of work to do. So as I said earlier, it's a challenge for the Idris elaborator because there's a large amount of type level computation going on, and it's meant we've thought quite a bit about when evaluation has to happen and how to do that evaluation. And so back in January when OHAD started working on this library and had the basics up and running, it was taking about half an hour to check the Frex library. So it was kind of painful to work with. And now, at least on my machine, that's down to about 15 seconds. So we've done some pretty significant performance work in developing this library. Which is fed back into Idris 2 in general, which is marvelous. But we still have this usability problem, so there's a lot of noise there. I think elaborator reflection might help. Perhaps if Frex and unification can somehow talk to each other, like the unifier could say, this is the problem I have to solve. Can we invoke Frex in order to solve that problem? So there's some potential there because unification introduces constraints, equality constraints, which are often of the form that you just need to provide a proof for. And then once we're done here, we'd really like it if other languages tried implementing the same thing. Because as I say, it's not Idris specific, it's something that could be applied to any kind of language where you're working with indices in data types. So there's a long way to go, but we have the basic machinery up and running, and we think this is going to make programming with indices much more pleasant in the future. So, thank you.